In this video, we'll be looking at how light was used to develop the quantum mechanical model and also how light affects electrons in general. Before we can do that, we need to talk about a little bit of information about light. Light is a kind of electromagnetic radiation, and electromagnetic radiation includes gamma rays, X-rays, radio waves, along with microwaves, ultraviolet radiation, and infrared radiation, among others. All of these types of radiation are going to travel at the same speed whenever they're in a vacuum, which is 2.998 times 10 to the 8th meters per second. And this is often abbreviated as C whenever we're doing math problems. One important feature of a wave that we need to look at is the wavelength, which is the distance between the crests of a wave. And so the crest is the top of a wave, and so we'll measure from the top of one part of the wave to the next time that it gets to the top again. In this image, we can see two pictures of waves. There's a question at the bottom of the slide. Which of these waves has a longer wavelength? We can also look at which of these waves has a higher frequency, which means which one oscillates more. An oscillation means how many times the wave will be able to crest or get to the very top of its wave cycle in a specific amount of time. The wave that we should have selected to have the longer wavelength is the first wave. And the wave we should have selected to have the higher frequency is the second wave. In general, we can see that the longer the wavelength of a wave, the less times it will be able to oscillate in a specific amount of time. This means that wavelength and frequency are inversely proportional because as one increases, the other decreases. To compare the speed of light, wavelength, and frequency, we have an equation. In this equation, we're using C to represent the speed of light, which we should have already recorded as 2.998 times 10 to the 8th meters per second. And that's equal to lambda, which is the symbol we've used to represent wavelength, and it looks like an upside down Y, which is multiplied by nu, which is the symbol for frequency that looks like a curved V. And we can see here that wavelength and frequency are inversely related. So whenever one goes up, the other goes down. There's an important note here at the bottom that says different frequencies of light produce different colors, and these create the spectrum. The most common spectrum that we can probably think of is a rainbow. Which is the spectrum that's created whenever white light is put through a prism. In the case of a rainbow that we would see in the sky after it rains, the prism would be the amount of water that's actually captured inside of the air. Here we see some problems that can be solved using our equation. The first problem says that it wants us to calculate the wavelength of light that has a frequency of 5.10 times 10 to the 14th hertz. In our equation, we have three variables, C, lambda, and nu. And we should start out this problem by identifying what each of those three variables are going to be equal to. C is actually a constant. That's our speed of light, which is 2.998 times 10 to the 8th meters per second. In this problem, it says that we need to calculate the wavelength, which means we don't actually know what that value is. And so that's what we're going to be solving for in this problem. But it does give us the frequency, which is 5.10 times 10 to the 14th hertz. hertz here being our common unit for frequency. Our common unit for wavelength is going to be meters. So to set up this problem, we have two variables, and we're looking for the other one. And so we're going to plug those into our equation. So our equation should look like 2.998 times 10 to the 8th meters per second is equal to lambda times 5.10 times 10 to the 14th hertz. To solve this, we're going to need to divide both sides by the wavelength, or by the frequency. And so if we divide both sides by the frequency, we're going to end up with a fraction that looks kind of like this. I'm going to move this down so we can see it a little better. Okay, so we've got the speed of light divided by the frequency is equal to our wavelength. And if we type this in our calculator, we should get 5.88 times 10 to the negative 7th meters, which is going to be our answer. Now, looking at our equation, since wavelength and frequency are both on the same side of the equation, that means solving for them is going to be a very similar process. Both times, we're going to know the speed of light because the speed of light is a constant, and all we need to do is put in the amount that we are given, which is either going to be the wavelength or the frequency, divide by that number, and we should be able to get our answer. And so, either way, solving the problems is going to be very similar. In this next model, we have a representation of the entire electromagnetic spectrum, which ranges from radio waves all the way to gamma rays. And there's a small portion in the middle, which is visible light, which we can see magnified here at the top to show us the entire visible light spectrum, which if we look doesn't actually take up very much of the entire electromagnetic spectrum. Looking at this spectrum that we have for visible light, we can see that it's a gradient. There's no specific bars of color where we have red, and then red ends and we get orange, and then orange ends and we get yellow. All of it blends in together. This is because each small variation in the amount of energy that we have is going to give us a different frequency. The energy affects the frequency because more energetic waves are going to have a higher frequency. So we have our low energy radiation, our low energy visible light, which is going to have a red color, and our high energy visible light is going to be on the violet end of the spectrum. Now, based off of its wavelength, we can separate light. Whenever white light, which is the light that you might see outside coming from the sun, is put through a prism, we get the full spectrum all the way from red to purple because all of those colors are mixed together to make the white light. And whenever they pass through a prism, they're scattered at a very specific amount, giving us a full spectrum all the way across. Note that this picture is not an accurate representation of what that spectrum would look like, because instead of a smooth gradient, we have bars of color. In an actual rainbow, there's no sharp transitions. It would be a smooth gradient all the way through. This is only true, though, for white light. White light contains all of the different colors of light. If we had a different color of light, then we would only have some of the colors show up whenever we put it through a prism. For example, whenever we have a gas, if we heat it up by running electricity through it, it will give off different colors. And if we pass that light through a prism, then it's going to give us specific colors that are being shown, but not the entire spectrum, because it doesn't contain all of the colors in the spectrum. Each element has its own characteristic color, which acts like a fingerprint to be able to tell which element it's going to be. We can use this to identify what atoms are in a specific substance. This is how we know what stars are made of. Stars are able to emit light, and by getting the characteristic colors of that light, we are able to tell what elements are in a star that are producing the different colored light that we're seeing, even though they're very far away. The specific colors that are emitted by each element are called the electromagnetic or the atomic emission spectrum. As we can see from these pictures, only some colors are actually shown because those are the only colors that are actually going to be emitted by that specific element. So here we see some more pictures of waves. Using the information that we have talked about in the last few minutes, say which of these waves is going to have the highest energy. We should have selected that the bottom wave has the highest energy because we can see that it's got the highest frequency. Remember, a long wavelength is going to have a low frequency and a low energy. That's what we see in this first wave here, where we have the longest frequency and we've got the lowest energy. The highest energy is going to have a high frequency and a short wavelength. Up until now, we've been treating light as a wave, but it can also act like a particle. We can treat the pieces of light as photons. And using this information, we can actually create another equation that relates energy and frequency. Now, as we saw in the previous slide, if we increase the frequency, we increase the energy. And if we increase the energy, then we increase the frequency. And so that means that these two are directly proportional to each other. So whenever the energy, which is symbolized by the capital letter E, and the frequency, which once again is symbolized by the Greek letter nu, are related, we're able to get this equation. Here we do have another constant, which we call Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds. So let's go ahead and practice using that equation. In our example problem, it says, what is the energy of light with a frequency of 5.10 times 10 to the 14th hertz? Now, looking at this, we can see that it's asking us for energy, so that's what we're going to be solving for. We already know what h is because that's a constant. So we can record that as 6.626 times 10 to the negative 34th joules times seconds. And in this problem, we were given our frequency, which is 5.10 times 10 to the 14th hertz. Now, once again, we have two of the variables, and we need to solve for the third. So we can just go ahead and plug these in. And we get E is equal to, we're going to put in Planck's constant, 6.626 times 10 to the negative 34th joules times second. And we're going to multiply this. We're going to multiply this by our frequency, which is 5.10 times 10 to the 14th hertz. Whenever we do that, we should get an answer of 3.37 times 10 to the 19th joules. Joules here being our common unit for energy. Previously in class, we learned how to write electron configurations. Whenever we write electron configurations, we're writing the electrons' positions in their lowest state of energy. Anytime we add energy, though, we are able to move electrons from a lower energy level to a higher energy level. Whenever electrons move from a lower level, which is called the ground state, to a higher level, they are said to be excited. And so we would say an electron that's moved from a lower energy level to a higher energy level is in an excited state. If we look here, we have a basic representation of the atom showing our energy levels as rings. On our first energy level, we have an atom, or we have an electron. We're assuming that this is a hydrogen atom because we only have one electron present in our atom. Since this electron is in the very lowest energy level, we would say that this is in its ground state. If we add some form of energy, like heat, electricity, or light, this can make the electron move to a different energy level. What's going to determine which energy level it moves to is how much energy is actually added to the electron. Whenever it moves to a higher energy level, we would say the electron is excited. The electron can't stay in its excited state, though. It's going to end up having to move back to the ground state. And whenever it does this, it's going to release the energy that it absorbed as a photon. This is what's going to produce the light that we see coming off of the electrons. There are different options for how the electron could fall back. If the electron's at a higher energy level and it's falling to a low energy level, it could take a few different steps to be able to get back to its original spot. It could fall down just a couple spaces and then fall the rest of them, take it about half and half, or it could fall down all of the energy levels all at once. If we have a few small jumps, we're going to release a few smaller amounts of energy a little bit at a time. If we make a bigger jump all at once, then we're going to release a lot of energy all at once. The further an electron falls, the more energy it's going to release, and the more energy gives us a higher frequency. It's important to keep in mind that this is a simplified explanation and doesn't take into account that different orbitals are going to have different amounts of energy. Not all orbitals are the same. For example, in the third energy level, there are s sublevels, which have the lowest energy. The p sublevel has a slightly higher energy, and the d sublevel is even higher than that. Depending on which orbital an electron ends up finding itself in, it could have a different amount of energy and then release a different amount of energy back out. That being said, all electrons can move around whenever energy is added. They can just jump to a higher energy level. The last thing we're going to look at is Heisenberg's uncertainty principle. A basic explanation of what this is says that it's impossible to know exactly the velocity, which we can think of as speed, and position of a particle at the same time. This is usually used to refer to electrons and applies to things that are microscopic. Remember here, microscopic means there are things that are too small to see with the naked eye. If we wanted to measure the position of an electron, we would have to add energy. And energy would change the speed of the electron in the atom, making it very difficult to actually figure out where the electron is going to be. It is currently thought to be impossible to know exactly the velocity and position of a particle because we can't measure one without altering another.